Hello, everybody. Uh, I hope all of you have a wonderful break and you have returned to campus or maybe to the courses uh, online with full of energy. So we are going to continue our discussion about encryption algorithms. And in this week, we are going to talk about asymmetric encryption algorithms. If you remember, we have talked about when we started this lecture, I've introduced you two big categories of encryption algorithms or ciphers. I said that our ciphers might be uh, symmetric or asymmetric. In symmetric cipher that you see here in this top image, we have only one key which is similar. I'm of course refreshing your mind. Many of you may remember this, but I'm refreshing your memory before getting into details of asymmetric encryptions. Okay, let's continue the refresh. Yeah, I was saying that in symmetric encryptions like here, both kind of sender and receiver, or at the encryption side and decryption side, we use the exact same keys. So you see these two keys are exactly similar. And anyone who has the key will be able to do both the encryption process and the decryption process. But in asymmetric encryptions or asymmetric ciphers, the story is different. We have two different keys. One of the keys is, which is called public key. It is good for only encryption. You can only encrypt, you can only lock your information using that key. And that same key is not good for decryption. For decryption, another key is required. This is called, sometimes people call it public key. And this one is called private key. So you may ask, so what is the reason that we are talking about, or why do we have asymmetric keys? Symmetric key encryptions are working and everything seems to be okay. Yeah, and symmetric key encryptions, they work, but we have a very big challenge, which is until now we haven't addressed that, and that challenge is to how to distribute key between the uh, parties or between the side of an encryption. For example, if we are in a network situation, we are in a network condition, and one side is Alice wants to encrypt something and the other one is Bob, they want to communicate securely. So there should be a key distributed between them. In all of the lectures we have had so far in this, all of the videos, sorry, we have had so far in this lecture number 3, we always were assuming that there is a key which is already shared, and sender or encryptor and decryptor, they have a key shared between them. But the technical question that you may ask is that who and how who is kind of going to share that key, and how are we going to do that? This is a time that asymmetric encryption algorithms played a role. We can use asymmetric encryption algorithms in order to share a key over a non-secure channel. So if the channel is non-secure, in that case, all symmetric key encryptions will not be able to work because they cannot share the key. So what the people do is that they use asymmetric key encryption, like, for example, we will be talking about two of them, RSA, for example. We will be using asymmetric encryption to share the key, and then after that we switch to symmetric key encryption, because symmetric keys are faster and they take less computation, and in general we can say that they're less costly. So people would like to share the only important part or the key using the asymmetric keys, and after the key is shared, people switch to symmetric key encryption. So this is the kind of refreshing your mind and talking about asymmetric versus symmetric key encryptions. And now we are going to, in this lecture, we are going to talk about two of them, RSA and Diffie-Hellman algorithms, which are both asymmetric key encryptions. But before that, I'm going to give you some kind of basics on the requirement or features that you would like to see in asymmetric or public key encryptions. First of all, it should be, we like to develop algorithms that preparing or generating keys in them is not very complicated. So key generation should be computationally easy. We don't want to come up with something that its key generation is very complicated and needs many cycles or many rounds and takes power and energy or computational power of our computer. So the key generation should be simple and easy. And this is what we see in, for example, RSA and also in Defiant, that the key generation is very easy. It should be computationally easy for the sender or encryptor to encrypt the message. You have something, you have a message or you have a file and you want to encrypt it, and you are authenticated individual and you have the public key. Because later we say that the public key is a key that it will be used for encryption, and the private key is a key that will be used for decryption. And we define them formally. We say how they should be derived for each algorithm. But anyway, this property says if I'm an eligible person, an eligible individual, and I have the public key available, it should be computationally easy or feasible for me to do the encryption. It should be computationally easy for me to decrypt the text or the ciphertext given the private key. If I'm an eligible or legit receiver and I have access to the private key, so this means that this message has encrypted for me, I'm the kind of recipient, or I'm the alleged recipient of this message, it should be computationally easy for me to decrypt and get to the plain text. In contrast, it should be computationally infeasible for someone who doesn't have the key to recover the original message. So it should be computationally very hard or infeasible for someone to break into an algorithm without having the private key. Also, it should be computationally difficult or infeasible for the attacker or the malicious person in order to determine the private key from the public key. We will be later showing this in detail, that public key is something that everybody knows it. Everybody has access to public key, and the private key is here the asset, the security asset that we should keeping it secure. So if I'm an attacker and I have access to your public key, it should be computationally infeasible for me to drive your public key. Okay. Based on these kind of features that we just talked about them, let's talk about two kind of math problem that will be helping us toward developing asymmetric encryption algorithms. One of them is called factorization. In factorization, we have a number like x, and we try to say that x is a multiplication of two things. For example, a times b. This is called factorization. If you give me x and I can find a and b in such a way that a times b equals x, I can claim that I could factorize x. This is factorization. For example, 12 can be factorized as 2 times 6, right? So this is the factorization process. And the reason we talk about factorization is that in asymmetric encryptions, we drive the keys in a way that we want to make the factorization very difficult. So let's take a look at the factorization given that we have two numbers. If we have two numbers like P and Q, which are large prime numbers, of course, all of you know that what are the prime numbers. Prime numbers like 2, 3, 5, 7, and so on. These are the numbers that they are only divisible to 1 and themselves, nothing more. For example, 7 is only, you can only divide it to 1 and 7. There is no other divider for 7, and so on. These are called prime numbers. So if I get two prime numbers like P and Q, which of course are big numbers, in that case, it is computationally easy to find N, which is the multiplication of P and Q, and it is computationally hard to find P and Q from N. For example, if let's say if we assume P is let me clear here so that I can. Okay. Okay. For example, assuming P is 5, of course, these are not large prime numbers. I'm just giving you example. And Q is 7. Finding 5 times 7 is not difficult for us. It's very easy. But if someone gives me 35 and asks me, okay, find the factorize 37, since 37 is the multiplication of two prime numbers, I would have only 4 divider for this divider for this number: 1, 5, 7, and 35. So, and finding these two is going to be very, 1 and 35, they are obvious, they're valid for any number. Of course, I'm not searching, I'm not seeking for them. So finding 5 and 7 for 35, it takes the maximum number of computation, because you don't have any of those rules. This is not an even number, so that you cannot say 2 is the divisor of this number. 3 plus 5, for example, doesn't equal to any coefficient of 3, so this number is not divisible to 3, and so on. So you need to, when I say you, I mean the attacker. The attacker will have to check every single number manually to see, for example, 4 times 7, does it equal to 35 or not, and so on. So it is computationally difficult. We're talking about, in parentheses, we are talking about prime numbers, for example, with 50 digits, with 100 digits. So it is, at the end of the day, very difficult for the attacker to find, to factorize a number which is the multiplication of two prime numbers. So this is the first thing that we will be using in asymmetric encryption. The other thing that we sometimes use it is discrete logarithmic kind of power computation. And it says given G and the number G to the power of X mod P, where P is a large prime number, it is infeasible to calculate X. If I give you G, which is a number, any number, and I calculate G to the power of some number X, and then take the mode of that to the power of, with respect to a number, prime number P, and give that number to you as well. For example, here I have something. G is 5. In my example, G is 5. And my X is 4. So I calculated 5 to the power of 4. And P, I assume 37. 5 to the power of 4 mod 37, it becomes 33. So now I'm gonna publicize 33 and 37 and 5. If you don't know the 4, and if you're seeking for 4, it's gonna be there is no way to mathematically drive that. The only way you have is to just come and calculate different powers of 5 and take the mode with respect to 37 and compare to see and seek to see which one equals 33. So it's going to be time consuming. So that's why we say it's computationally infeasible. Of course, we are again talking about the cases that the prime numbers are very big. Okay, based on these two type of mathematical tools that we define, these are tools that we will be using, and we showed that it's going to be difficult if the input numbers, if the prime numbers are chosen big enough. Let's talk about the algorithms. We will be talking about RSA algorithm, which was developed in 1977 by a group of 3 researchers at MIT, Massachusetts Institute of Technology. And it is a block cipher, of course. It takes a number and kind of encrypt them in a block. And it takes the plain text as a number, as an integer number. We will be talking about it. And the second asymmetric encryption we will be talking is called Diffie-Hellman, which is proposed by Diffie and Hellman, 2 researchers. And we'll see that this one is specifically designed for key exchange. So it is a very good thing for exchanging keys between 2 parties. Okay, let's focus on RSA. Now, starting from this slide, I'm going to focus on the RSA, and I'm going to talk about specifically about the RSA. First, I define how the algorithm generate keys, because this is very important. We have talked about 2 types of keys in asymmetric encryptions, public key versus private key. We should say first how the algorithm generate keys. That's the first important thing that we will be talking about. And then after that, we will be talking about how the algorithm encrypt and decrypt. Okay, this is how the algorithm generate keys. Algorithm starts with choosing 2 big random prime numbers, P and Q. And then we compute N, which is P times Q. And then we also compute phi of N, which is computed as P minus 1 times Q minus 1. An integer E should be chosen with these 2 properties. E should be selected from 1 to phi n. It should be smaller than phi n and greater than 1, and also it should have the greatest common divisor of 1 with respect to phi n, which means that E and phi n should be co-prime. For example, if your phi n, let's say, is assuming that, again, let's return to our example numbers, assuming 5 and 7, here phi n will be 4 times 6, which is 26. Of course, these are very small numbers, are not good for encryption. I'm just giving you an example. Your E should be something between 1 to 24, but of course you are not allowed to use, for example, E of 8, because 8 and 24, they have the greatest common divisor of 8. 8 is a divisor of 8 and also 24. So 8 is not allowed. It's not a good number. It's not allowed to be picked as E. So E is a number between 1 to phi, and with these 2, with this property that greatest common divisor of E and phi n is 1, and then having E and phi n, we find it D such that E times D mod phi n equals 1, which means that E times D is co-prime with phi n. So after generating E, phi, n, and D, sorry, E, n, phi, n, and D, we will be using E and N as the public key, and D is our private key. So based on this, now let's talk about encryption and decryption. We said E, E and N are public key, and D is the private key. So the encryption is very easy. It's just power computation. Of course, in modulo n, whatever we are talking here is a modulo arithmetic. We are talking about modulo arithmetic. It's not a normal power. For example, when you take the power, it's not going to enlarge your number because you're working on kind of under restriction of these module computations. Anyway, the encryption works this way. We have a message M, which we need to convert it into a number, and the message M, our message, which is this is our basically our plain text. So let me write it. This is our plain text. Our plain text should be a smaller than n, which is a multiplication of the two prime numbers. And we encrypt it this way. We just take the m to the power of e mod n. This is the encryption process. That's it. This easy. You just take the m to the power of e and take the remainder in the module n, and that's going to be the ciphertext. That's going to be our ciphertext. And the decryption, so you see here E is used. E, which was our public key, here is used as in the encryption process. In the decryption process, we will be using D, which I said this is our private key. And of course, in the decryption side, we have ciphertext. We have received the ciphertext C. So we take C and we take C to the power of D. We calculate C to the power of D, of course, in modulo n. And this means that C, we just calculated here. We said that C equals m to the power of e. So this is m to the power of e. So instead of C, we put m to the power of e. So I get m to the power of e to the power of d, because for decryption, we take the ciphertext. This is the ciphertext. This is the ciphertext part. And we take it, take the power of d of it. So it's gonna be m to the power of ed mod n. There is a kind of theorem here that I'm not going to go to details of that theorem, but that's called Fermat theorem, Fermat-Little theorem. If you look at this theorem, it's not a complicated one though, but I thought it might not be of the interest of our class. So I didn't put the theorem here, but that theorem proves that e to the power of md mod n equals m mod n. And remember, m was our plain text. So if you take the m to the power of ed, which is basically ciphertext to the power of c, if you take the ciphertext to the power of d, which is m to the power of ed, based on the Fermat, based on the Fermat theorem, we get m mod n, which is our plain text. So this is how the RSA algorithm works. I'm gonna give you show you two examples on to see how the algorithm works. But one thing to remember before looking at the examples is that, of course, this algorithm, RSA algorithm, is works based on the numbers. We are talking about taking the power, some power of some number. And here the message, the ciphertext and plain text are not messages. So you may wonder, for example, I have this message, hello world, and I'm gonna encrypted using RSA. How am I supposed to do that? So easy way we can take, for example, the ASCII code of the every character we have here. For example, hello world. This is the ASCII word of H, ASCII word of E, L, L, O, and so on. And we can just, for example, just concat them to each other. So you see here 48 appeared here, and then we have 65, 65 is here, 6C, 6C, another 6C, 6F, 20. And then of course, this is a big number. It's a, of course, in hexadecimal, we are talking about hex. And we can convert it into decimal. In decimal, it's gonna be this number. And now we can start the encryption based on this number. And the same thing, we do the same thing when we want to do the decryption. After decryption, we get a number, and that number will be kind of recovered to a text using the reverse operation. So we first take its hexadecimal, we first convert it into hexadecimal, and then every 2 hexa digits will be considered as a code of 1 ASCII character, and then we convert them to ASCII letters. Okay, here is another kind of way of showing this encryption algorithms, RSA encryption algorithm that you see here. We select P and Q, and then P times Q is calculated, we call it N, and then phi N is calculated, which is P minus 1 times Q minus 1. And then we select integer E such that E is smaller than phi N, greater than 1, and also the GCD of phi N and E equals 1. And then we calculate D such that D times E mode phi N is 1. And then we are good to go. E and N are used as a public keys, and D and here in the book it says D and N, but N can be public. So I would say D. I would prefer saying D. D is the private key. And the encryption process, decryption process, based on what I kind of talked about. Okay, again, here is the same thing in a different plot. So it says that we have Alice, sender or encryptor, and we have Bob. These are the kind of classical names that is kind of widely used in encryption. Alice is trying to send something securely to Bob. So Alice will be using E and N as a public key and calculate P to the power of E mod N, send this over the channel, and then Bob receives ciphertext C, and C to the power of D mod N is gonna be the plain text, or recovers the plain text, which is P, and Bob will be using. Okay, now let's see examples I mentioned. The first example here, we have the plain text 88, and we have the public key 7 and 187. And here our private key is 23. So 88, we get the 88. We calculate 88 to the power of 7 mod 187. And it's gonna result in 11. But you may wonder how these big powers and big mode operations are going to be done. There are many theorems and there are many algorithms that helps us or help the computers to do that. We don't have to do it like a normal power computation. We don't have to, for example, calculate 88 times 88, blah blah, and then start doing the mode. Start doing the mode process. We don't do that. We don't do it that way. There are algorithms for modular arithmetic. So we have modular modular sum, modular subtraction, modular multiplication, and modular power, which are, of course, very easier than doing it in normal. Okay, this is the 11 that we send it mm, over the channel or over the medium, whatever it is. And then here we are using 11, we are kind of doing the decryption. 11 to the power of 23 mode 187, which again gives us 88. So we encrypt the 88 to 11 here, and we decrypt it to 88 using the private key. Here is another example with a kind of more details. It gives us kind of P and Q, assuming that P is 101 and Q is 113, so that we say N, which is P times Q, is going to be 11,413, and phi N will be 11,200. And of course, phi n is not a prime number, and we can factorize phi n, and that's how they make the factorization and powers kind of easy. So we choose E so that E is something between 1 and phi n, so it should be something smaller than 11,200. And it should have the GCD of 1 with respect to phi n. So here we use E of 3,533, and then we compute D in a way that E times D mode of this number is 1. So our D is 6597. This is the D that we have calculated. You remember we said that D times E mode phi n should be 1. This is a property that we should satisfy when choosing D. So this D kind of fulfills this requirement. And then it comes to encryption. This is a public key, 3533 for Bob, and this is a private key for Alice. And here Bob and Alice are swapped. Bob is the kind of recipient. So this is a public key of Bob, and once Alice wants to send something to Bob, it uses the Bob's public key. So the message we have, for example, let's say this is the message. So the message should be powered to the public key of Bob. So we calculate 9726 to the power of 3533. Of course, mode 111 413, which is our N. So this is going to be our ciphertext. This is a C, or our ciphertext, which is our message to the power of E. Yeah. And then Bob receives this number, which is the ciphertext, and uses its private key, which is 6597, and calculate this and takes the power of ciphertext to that number. I think here, yeah, here Bob at the recipient side calculates the ciphertext received, which is 5761 to the power of its private key, which is 6597, and based on that, Fermat's little theorem, I told you that this is gonna be equal to 9726 to the power of this number, which again becomes this. So this way, Alice can send the message to the Bob. Okay, and this is the RSA algorithm. That's it. We are just done with the RSA algorithm. But I'm also willing to talk about some security weaknesses of the RSA algorithm. First of all, brute force attack that that requires the attacker to come and sit and compute all the possible keys or the possible private and public keys is going to be infeasible. We just talked about it, that if the input or initial prime numbers are chosen big enough, it's not going to be easy to do factorization. It's not going to be easy to do logarithmic power operations. So it's going to be very difficult or computationally infeasible for the attacker to do the brute force. So in terms of brute force, if we just pick big enough prime numbers, we should be okay. But asymmetric encryption algorithms are always subject to mathematical attack. What does that mean? It means that mathematicians may sit and may find ways to do factorization easier, and that avenue is always open. We can never ever block that avenue, saying that okay, no one can come up with something. There might be some ideas, and if they come up with those ideas, if they develop something in math that make the factorization from the math standpoint easier, the RSA algorithms or any other encryption algorithms, I mean asymmetric encryption algorithms, that they are based on use of prime numbers and factorization process, they're going to be under danger. So this is another type of attacks that we can talk about or we can consider. Another class of attack that I will be talking about, this specific one, and I'll give you at least one example, is called timing attack, at which people try to use side information in order to attack the algorithm. Timing attack is a type of attack that it actually looks at the execution time of the algorithms, and by looking at that number or the execution time, the attacker tries to get some information and make some guesses that guesses are very close to the real numbers we use. And then the last class or category of attacks on RSA is called chosen ciphertext, which means that the attacker tries to exploit properties of the or features of the RSA algorithm, which again is pretty much we are safe, because if the prime numbers are big enough, we are safe. Okay, the factorization operation or process, as you saw, is very important, and RSA algorithm is heavily relying on the fact that it on the assumption that factorization is infeasible, or given n, it is very difficult for the attacker to find P and Q. If P and Q are big enough, the developers of the algorithm, they assume that okay, it shouldn't be easy for the attacker to find P and Q, which I mentioned. We call this factorization. This is true, but at the same time, in order to show the available capability of kind of attackers, RSA laboratories, they have kind of initiated a challenge. It is called RSA factoring challenge, and they kind of give some prizes. They announce some prizes for everyone who can break some n's. Basically, they give you the n and they ask what are the P and Q. Of course, the n is very big and they ask for P and Q. And here are some of the kind of results of this challenge. It is interesting. You can go online and search for factoring RSA factoring challenge, and you see the prizes, the number they paid. For example, in some years they paid up to $50,000 for the winner, and some days less or a little bit less than that. But I mean, they are really serious. They want to see if someone is capable of breaking and doing the factorization. And the results are also at the same time interesting. Uh, for example, in latest broken in 2009, attackers could, or here people are not attacker basically, they are researchers or kind of cryptography person that they try to do the factorization, but they were able to factorize n that had 232 digits. So we are talking about a very big number, a number with 232 different digits. And when you convert it into binary, it is something about 800 bits. Such a big number. In December 2009, researchers were able to break that and could factorize that number into two prime numbers. You may say, okay, so in that case, how RSA is secure? The answer is this is done, but the price of doing that is very expensive. So basically, it is not feasible for everybody. It is not doable for everybody to go and just quickly break an number with a number this big in, for example, 1-2 hours. No, they could break it, but they took a lot of time and energy. They used supercomputers to do that. So they did it, but at the same time, it doesn't mean that they did it easily. It cost them a lot, but this challenge is still open, and even now some of the other kind of complicated or advanced version of these challenges there. They have announced some numbers and they are waiting for the factorization. But as a summary, I should say here that threats regarding factorization, they come from two kind of avenues. First is the continuing increase in the computational power we have. Every day we see that more powerful computers are out, and kind of computers with 16 cores processors, 32 cores processor, and so on. Even supercomputers, they are getting improved every day, every month, and that means that our computational power is increasing. And the higher computational power means that it's going to be easier for an attacker to do the factorization. But the second avenue, which is sometimes even more dangerous, the reason I say more dangerous because it is less predictable, is that there might be some algorithms or some math development that make factorization easier. This happened over the past 20 years. Multiple algorithms have been introduced so that they help the factorization process. They help, and once they come, for example, they make the factorization from O(n) to, let's say, for example, O log n. And you know what this means. This means that you don't have to, for example, search whole space from 1 to the number that you have. You just need to go from 1 to the log of this number, which of course is way smaller than the number itself. So this is the second avenue that we should be also considering when we talk about the computational or security of factorization-based encryptions. Okay, now I'm going to talk about timing attacks. Timing attack is also something that I said I want to talk about it. In one researcher called Paul Kocher, he used a totally different kind of information in order to attack RSA. And he showed that the RSA can be broken using that information. And that information is not something about the key or factorization or something like that. it's about the timing or the time that algorithm requires to do some power computations. So if what he did, he just looks at the processor, the microprocessor, and measures the amount of time that the processor needs to do that factorization operation. Of course, he doesn't have access to the actual P and Q, but at some point for RSA, you need to, for example, calculate P times Q. So this P times Q, it gives you, and the amount a processor needs to do this computation, the amount of time processor needs to do this computation, it tells you something. So based on that, you can, if you have that number, you can try different things. Of course, I'm not giving you the details of the attack, but the attack uses this side information that people also call it side channel, uses the side information in order to bypass a large number of possible keys, or using the side channel or side information, they reduce the key space to the biggest extent, and they can kind of break the algorithm. So this is important because it comes from a totally unexpected kind of direction, and it only looks at the ciphertext. It doesn't need to have any information about the, for example, PQ, public key, or private key. Multiple kind of countermeasures have introduced for that. For example, constant exponentiation time. They say when you want to do the exponentiation or multiplication, change your system or modify your system in a way that all multiplications or exponentiations, they take a unique amount of time. So regardless of the value you're multiplying P times Q, or you are taking the exponentiation of second power of Q or whatever, regardless of the value, it should take always the same amount of time. The reality is, when processors want to do that, the amount of time that it takes for a multiplication or for exponentiation, it is heavily related to the values. For example, if one of them is 1, the multiplication is going to be very easy. Or if one of them is 0, or if one of them is something of power 2, the multiplication is going to be easy. So the processor, the time that the processor needs to do a multiplication or exponentiation, it depends on the values. But here they say kind of break that property and change the system. It might be the processor or it might be the code, in a way that any exponentiation or any multiplication takes same amount of time. And this way, the attacker will not be able to understand or will not be able to conduct the attack. Or add random delay after any exponentiation or multiplication operation. You add a random delay so that delay will be added to the time of the actual time of that operation, so that the attacker, for example, it took, let's say, 100 microsecond, and you also add another 23 random. So and the results will be kind of made made available here. So attacker will be kind of fooled, and attacker will be misled. Attacker assumes that, okay, this operation took 123 microsecond, although it was actually 100, but we changed it. So this is called a random delay, addition of random delay. And the last countermeasure, it says use blinding. Multiply the ciphertext into a random number, and then start doing the encryption. Since you are not working on the actual ciphertext in the decryption process or in the encryption process, the timing measurements are going to be all messed. So whatever your plain text is, let's say is 1, 2, 3, you multiply it by a random number, and of course you know that random number, and every time you change it. For example, 7, you multiply it by 7, you get a number, and then you start multiplication using this. Sorry, encryption using this. Everything here takes some time, and you get the ciphertext. And then again, you decrypt the ciphertext, you get some numbers, and of course, at the end of the day, you need to divide it by 7. But here, everything is with respect to this text, which is the modified version of our plain text, not the original plain text. So the timing measurements here are not going to help the attacker. This is another approach or another countermeasure proposed for dealing with timing attacks or timing side channel attacks. Okay, we are done with RSA encryption, and now I'm going to talk about Diffie-Hellman. Diffie-Hellman algorithm is another asymmetric encryption algorithm, and it is kind of introduced or developed particularly for key exchange. You want to exchange keys. Of course, we can do the key exchange using RSA as well. Two parties want to send something, and the key, let's say this is Bob and Alice. Bob and Alice are willing to start a secure communication. They use RSA in order to exchange the key. So Bob generates a key encrypted using RSA and send it to Alice, and Alice receives and opens the key. So both of them now they have the key. And now after sharing the key, they don't need the RSA. They switch to, for example, AES, and they transfer the actual amount of data, the bulk data, using AES or DS or whatever. So we need to have a combination of RSA plus AES for establishing a secure connection between the two parties while the channel is not secure. But here in Diffie-Hellman, we will not be using RSA. We use Diffie-Hellman, and here we can exchange the key using Diffie-Hellman very easier, because it's in terms of computation, it has less computations with respect to RSA. The way it works is shown here in this right plot, right, that shows the blocks, kind of how the Alice and Bob, they wanna, how Alice and Bob, they want to kind of exchange the keys. They use some keys called YA and YB, keys of Alice and Bob. And at the end of the process, they reach to a same key, which is the key that we wanted to share it. So this is a key that Alice and Bob will be using it hereafter for that symmetric encryption. So it works based on some kind of operations between Alice and Bob, and it is based on finding a primitive root, which is defined here. A primitive root is a number that here is a definition. Of course, I don't want to add too much math to the lecture, but we need to know, we need to at least hear the definition. In modular arithmetic, G is defined as a primitive root modulo n if every number co-prime to n can be somehow written as a power of G. For example, here we say in modulo 7, 3 is a primitive root, because everything in modulo 7, every number in modulo 7, of course, when I say every number, I'm not talking about all numbers. I'm talking about 0 to 7, 0 to 6, because we are in modulo 7. 0, 1, 2, 3, 4, 5, 6, and 6. These are all kind of remainders that we may see in modulo 7. Anything 8 123, whatever, they all will be mapped into one of them. So we only have 7 numbers in module 7. And anything in module 7 can be written somehow with respect to as a power of 3. So for example, 3 itself is 3 to the power of 1. 2 can be written as 3 to the power of 2. 6 is 3 to the power of 3. 4 is 3 to the power of 4, and so on. So that's why we say that 3 is a primitive root in modulo 7. Okay, the Diffie-Hellman algorithms works this way. It says you get a q, a number q, which is a prime number, and you need to find a primitive root for q, modulo q, that we call it alpha. So we get two numbers, q and alpha. Q is the prime number that we start, and alpha is the primitive root of that q in modulo q. Of course, alpha might be an even number, might not be. Alpha might be sometimes it is even number. So it doesn't mean that it is always odd or prime. Anyway, the algorithm works based on q and alpha this way. It says select a private XA. We are talking about Alice at the Alice side. So we have, if you remember, we have 2 sides, Alice and Bob. Alice and Bob. Alice selects a number called XA, which is smaller than Q. And this is gonna be the the private key of Alice. Alice also calculates something based on this XA, which is here, alpha to the power of XA, modulo Q, of course. And this is called YA, which is the public key of Alice. The same operation happens at the Bob side. Bob finds a private number for itself. It calls it, Bob's call it XB. XB, of course, is a number smaller than Q. And Bob calculates alpha to the power of XB mod Q and call it Y of B. Okay, the 2 parties now, they change their Y's. It means that Alice sends YA to Bob and Bob sends YB to Alice. And then the rest of this will be this. At the this is something at the Alice side. At the Alice side that Alice has received YB, it calculates YB to the power of XA. XA is the Alice private. So it has its Alice has its own XA. So it calculates Alice calculates YB to the power of XA mod Q, and Bob calculates YA, which receives from Alice, to the power of XB, which is his private, to the power of YA to the power of XB mod Q. And the interesting part is this, that YB to the power of XA, which is being calculated at the Alice side, equals YA to the power of XB, which is being calculated at Bob's side. And this is gonna be the key that they are going to agree upon and they will be using hereafter. Here is example. If Q is 353 and alpha is 3, let's say Alice picks 97 and calculates 3. So Alice picks 97 and calculates 3 to the power of 97 mod 353. Bob's picks 233 and calculates 3 to the power of 33 mod 353, it gets this number. This is something that Alice sends to Bob. So, and this is the number that Bob sends to Alice. So they exchange these two numbers. And this can be sent as a plain text. We don't care. They are not, from the security standpoint, it is okay if the attacker accesses these numbers. Okay, in the next step, Alice has received 248 and calculates 248 to the power of her own key, which was 97 mod 353, and Alice gets 160. Bob also does the same thing using the kind of public key he received, which is 40. So he calculates 40 to the power of his private 233 mod 353 and gets the same number, which is 160. So this is how they share a key and agree upon a key. And hereafter, this 160 can be considered as a key that both of them, they have it, and they can work upon it. Okay, I think that should be enough for today. Please use Diffie-Hellman, the way written here with uppercase D and H as the attendance code for this lecture. And we continue in the next video, and we'll talk about some attacks, and also we talk about digital signatures and digital certificates. Thank you for attending this class, and have a good rest of the day.